All right, today we're going to dive into something really cool and, honestly, a little weird. It's a method for finding the hidden building blocks of a number, and it's called the Lewis Sieve. Think of it less like a math problem and more like a detective story.
Every number that isn't prime is made up of smaller prime numbers, kind of like a secret code. But how do you actually crack it without just, guessing? Well, we're about to look at a method that turns this whole thing into a hunt for patterns.
So, our target, our person of interest, if you will, is the number 143. Looks pretty harmless, right? But it's got prime factors hiding inside. And we're going to find them. Not by throwing stuff at the wall to see what sticks, but by following a very specific and pretty fascinating set of rules.
Okay, so let's get started. Our investigation begins right now. We're going to peel back the layers and see what makes this whole thing tick. So here's the first rule of the Lewis Sieve, and it's a bit of a curveball. We don't actually start with 143. The first thing we do is double it. Now, why on earth would we do that? Well, by starting higher and working our way down, we're basically creating a bigger canvas. It gives the echoes and the rhythms of the real factors more room to show up. So, burn this number into your brain, 286. That's our starting line. From here on out, every single thing we do is going to be a step down from this point, getting us closer and closer to cracking the code of 143. And just like that, the hunt is on. We're moving down from 286 number by number. And with each step, we're going to see what dividing by powers of 2 shows us. The whole goal here is to spot the clues, the patterns, that are going to lead us right back to the factors of 143.
This is where the real detective work kicks in. We're not just crunching numbers here, we're on the lookout. We're actively hunting for those patterns, those little rhythms and repetitions that are going to crack this case wide open.
And what's wild is how quickly we start seeing results that are so tantalizingly close to our original number. I mean, look at this. At 282, we get 141. A little further down at 278, we get 139. We haven't found the factor yet, but you can feel the sieve already starting to zero in on it.
So what's causing all these numbers to break down so easily? Believe it or not, so far, it's just the power of 2. The source material has this great line for it, calling it primal slaughter, because even with just this one simple tool, we're already revealing so much of the hidden structure underneath.
Okay, check this out. This is a perfect example of the kinds of patterns that start popping up. Just look at the numbers that are divisible by 8. At 280, we get 35. You go down to 264, you get 33. And then at 248, it's 31. You seeing the rhythm here? And that, right there, that's our first big clue. The gap between 280 and 264, it's 16. The gap between 264 and 248, also 16. And each time, the result of our division drops by exactly 2. See? This isn't random noise. It's a predictable echo inside the sieve. This is the kind of stuff we're looking for. But these simple patterns, they actually lead to something even deeper, something way more dramatic that happens inside the sieve. The structure doesn't just repeat. Sometimes, it completely collapses in on itself. Let's just hit pause for a second on the number 256. This number is, well, it's special. As a pure power of 2, it does something pretty spectacular when we run it through our sieve. What we see here is what the source calls a wave collapse. You can divide 256 by 2, then divide that result by 2, and again, and you just keep going all the way down until you're left with the prime number 2 itself. It's this beautiful, complete cascade. And yeah, the source material just says it plain and simple. It is cool. It's this moment where the entire structure of a number is just laid bare in one clean, beautiful process. It's a pure expression of the power of 2. And get this, it's not a one-time thing. A really similar collapse happens when we get down to 224. That one's divisible by 32, that's 2 to the 5th power, which then reveals the prime number 7. These collapses are like major landmarks on our journey down the sieve. All right, we've seen the patterns, we've seen these wild wave collapses. With everything we've learned, it's time to close in on our original target, the factors of 143. The moment of truth is getting really close. Okay, our countdown continues. We go past 220, down past 212. The results are getting smaller and smaller as we get deeper. And then we land on 208. There's something about this number. It just feels significant. Let's take a closer look. Could this finally be the one that cracks the whole thing open? And there it is, 208 divided by 16. And what do we get when we do that division? We are left with the prime number 13.
Bingo. That's it. That's the solution we have been hunting for this whole time. The sieve, through this whole winding path of patterns and collapses, has just handed us one of the hidden prime factors of 143. It's 13.
So we found the factor. Awesome. But what does this whole process really tell us? Let's zoom out for a second and look at the bigger picture. Okay, so here's what you should really take away from all this. First, yeah, we found the factor 13. And from there, a quick division, 143 divided by 13, gives us the other factor, which is 11. But here's the really important part. The Lewis Sieve didn't just spit out an answer. It showed us the hidden rhythms, the structure inside the number line. It completely transformed the boring, brute force task of factoring into this elegant hunt for patterns.
And really, that leaves us with one final thought. If a strange little method like this can uncover such intricate structures just by counting down and dividing by 2, it really makes you wonder, doesn't it? What other hidden patterns, what other secret codes are just waiting to be discovered inside the numbers that build our entire world?